Hi guys, today I want to talk to you about the level shifter because there are circuits which are very used in both analog and digital electronics as well. So let's start with the level shifter. We will talk first about the non-inverting configuration. So let me use the inverting configuration. And the inverting configuration is basically this. You can use both NPN or NMOS for this. The NPN is basically having a signal here, a resistor, and just a pull-up with the desired voltage VH. And that you're gonna have the same voltage, but the same square waveform between 0 and VH, with only difference that it is inverted with respect to the input side. What about the MOS instead? Well, for the MOS is the same circuit, but there are some things that you have to take into account. And it is basically a parameter called QG, the gate charge. Whenever you are doing this kind of transition, remember that the signal here has to charge the GGS of the MOSFET. And I can show you in LTSPice what are the difference. So let me put an NPN, and let me put just a signal dot param d equal to 0.5 and dot param d, fs equal to 1 kHz. So you are supposing that here you have a square waveform between 0 and 1 volt with a rise time of 10 nano and a period of time of d over fs. And the period is of course 1 over the switching frequency. Nothing new under the sun. Now let's just put a 1 kilo ohm resistor. This is not, by the way, this is not a power switch, so you don't need to worry about designing the gate resistor or the base resistor here. And now you can put the pull-up resistor. Let R pull 1. Let me put a 4.7 kilo ohm pull, and let me put a way higher voltage like 5 volts. And so this will be the output voltage out 1. Now let's immediately use the same configuration to do but with the MOSFET instead. So let me put a MOS here, and let me change the name of the net, out 2, and let me put the first MOSFET of the list so that we can make immediate a comparison. Let me just switch for 10 milliseconds. No, 10 milliseconds no, because I wanted to increase the switching frequency. 2 over fs. So okay, as you can see, this is the NPN, and you don't find any problem with that. And this is the MOSFET. Oh, so something is happening. And what is the problem here? The first problem that we have with the MOS is that you have to remember that the NMOS is a voltage controlled switch. So meaning that you have to provide the input voltage Vin must be greater than the threshold voltage VTH. Otherwise it's off. So you have always to remember that. So the first thing that you're gonna notice is that here the MOSFET is not turning on, and so it can work for low signal levels. For this purpose only, I will put here 2 volts in both sides. So this is the first disadvantage that you are gonna see. Now with 2 volts it should turn on, and no? Really? Ah, okay, now it's turning on. So as you can see, I don't know what is the threshold of this, but it can be quite high. VTO 2.9, maybe it is this. Maybe. V threshold, voltage threshold. It can be this, 2.9. So if I put here 2.8, you won't turn on? Seriously? Okay, it does turn on though. So it wasn't that. My god. So you have to provide at least 3 volts to turn on this guy. Okay, let's skip for that for now, and let's see immediately the difference. So here, as you can see, there is a very big, there is a very low rise time, and that's it. That's because mainly you have to charge 36 nanocoulomb of charge here, and so if you lower this value like this to 4, you should have a way faster waveform, as we expect. So let me put the same here. Let me put out 3, and let me put the previous MOSFET with the higher gate charge, so that you can appreciate the difference. Okay, so now you see it. In the first MOSFET, you have lower gate charge, meaning that the gate current that we have to provide is of course less. So you can see that by zooming on the current here in the gate in the first case and in the second case. So here you can see that in the green curve is how much charge you're going to provide. Remember that always the equation that Q is equal to the integral of 0 and t of I t in the t. So meaning that if you are seeing the a current graph like this, it means that the area under this curve here is gonna be the integral. So it is reasonable to assume, let me put this on paint, it is reasonable to assume that here the integral is higher, and so you can see that here all this charge, all this red area that I'm coloring, it is exactly the gate charge that you're going to provide. And so if you do between 0 and this time here 0.5 milliseconds, and this is not this is the integral of it should be something like 1 over x, so it should be the logarithm of something. I honestly don't remember the integrals, but you can check the gate charge with this. So let's just say that we are we are discovering new things about the MOSFET that maybe you didn't know. So the first thing that you have to remember that this is a voltage control switch, and of course if you don't provide enough voltage even for the signal, it won't turn on. And secondly, you see that the MOSFET is way slower than the NPN, because you don't have to charge, for the signals, you don't have to charge the gate charge, of course, the gate capacitance. Secondly, so it is dependent from the gate charge. This has 9 nanocoulomb, and this is a 36 nanocoulomb. Get rid of this graph, and so as you can see here, the non-inverting level shifter, the winner for the inverting level shifter, the winner would be this guy here. But what about if you want a non-inverting level shifter instead? How can you do that? Well, there are two solutions. The first is to use this one again, and to use another one here, like this. By now you should have realized that you can even design logic gates with this, and so in many application notes you can find how to design the logic gates. You will discover that also this is called the NOT gate, because if you have one here and you put a transistor like I did with a voltage here, you're gonna have 0, and of course if you put 0 you're gonna have 1 here, so this is even a NOT gate. I will cover the gates in another video. So now if I look to this output here, the output is non-inverted. So let me use this. Here it is inverted, but here it's not. So yeah, you have between 0 and 5 volts, as you expect a level shifter should behave. So now let me use another configuration for the level shifter, so non-inverting level shifter, and this is called the Commong gate level shifter. The Commong gate level shifter, it's quite common in the most professional circuits. And how can you design that? Well, basically you have to put in a Commong gate configuration, you have to put the low signal from the source side, like here, like I'm doing right now, and you have to put the same amount of voltage here, which is typically hard to find in some cases. So in this case I will put 2 volts. You can even use a pull-up, yes, 4.7 kilo, and let me put here 5 volts like I should. 5 volts with a pull-up of 4.7 kilo. If you do run the simulation, you will discover that again you are gonna have between 0 and 5 volts, exactly like this. So now let us play with this circuit, and let's increase the switching frequency. Is the circuit fast enough to follow it? So as you can see, the MOSFET is let me call this 9 nanoC, 36 nanoC, and let me rerun the simulation. So as you think, the 9 nanocoulomb MOSFET is providing a good level of translation, but the 36 nanocoulomb is way past salvation. So this here doesn't stand a chance with a signal of frequency of 10 kHz. Instead, the first output voltage, the first MPN, still holds the ground. So it is still quite good. For what regards the non-inverting level shifter, they still win the fight. But oops, there is just a delay here, which is not so beautiful. So there's gonna be some problem here in the Common gate level shifter. So let me call this net CG, which stands for Common gate, and NI as non-inverting. And let me rerun the simulation so that I can identify the nets, NI and the CG. So the CG is gonna have some problems in the rise time, because for the parasitic capacitance that he's gonna see. So for now, the winner is the inverting level shifter with just an NPN. Inverting level shifter. What does it change if I change the pull-up resistor to, for instance, 100 kHz, 100 kilo? Well, it changes the rise time of this guy. It becomes slower. So remember that the weak pull-up, for instance 100 kilo, less dissipation, but is lower. strong pull-up, like 4.7 kilom, more dissipation, but faster. So for this reason, I'm using the lowest pull-up possible that I can even imagine. But remember that you can't put 1 ohm as a pull-up, because if you put 1 ohm as a pull-up, when this MOSFET conduct, it will have the it will make a divider, so you don't have the translation, but you're gonna have a divider. Because normally speaking, how does it work, a level shifter? So basically it becomes a short circuit here, and so you're gonna have not precisely a short circuit, but a divider between RP and the RDS on of the MOSFET or of your transistor. And so you're gonna have basically a divider here, VO, and VO is equal to V in times, sorry, not V in, sorry, you're gonna have basically a divider like that, like RP and RDS. And so this is 5 volts, and so you're gonna have VO equal to 5 volts times the MOSFET resistance over RP plus RDS. Now, since this MOSFET resistance is very low, this goes immediately to 0, as you can imagine. But if you do put a pull-up of 1 ohm, what is going to happen is that basically, let me put again a switching frequency of 0.1 kHz, so you can immediately see, is that basically you're going to have a non-zero voltage during the divider. So you're going to have basically VO, which is equal, for instance, to 5 millivolts. And this is not good because it will provide a lot of dissipation for your switch. If you, as you can see, I put 1 ohm here, and it is very despicable. So you don't want that. You don't want to do that. At least 1 kilo as a pull-up. If you, with 1 kilo, you are safe to assume that you don't have any voltage in the off region. This is also important. So the pull-up resistor must be greater than 1 kilo, 4.7 kilo, 7 kilo, but you don't want a pull-up so high either, so it must be less than giga ohm or even mega ohms. So if you put 100 mega ohms as a pull-up, it will become incredibly slower, and it won't even work, because here is not passing enough current, so it doesn't make any sense. 1 mega ohm, maybe it can work, but it is very, very, very slow. So 4.7 kilo ohm, and you should be right. Let me return to the common mode, common gate, and the non-inverting level shifter. Let me increase the switching frequency to 100 kilohertz, and let me run the simulation. So as you can see, the 36 nanocoulomb is beyond salvation, because again it is charging charging the CDS. The 9 nanocoulomb is still holding the ground, but not so well. But instead, what is winning right now is the inverting level shifter, because it has just one MOSFET, and instead the non-inverting level shifter starts to lower the performance. But as you can see here, there is some sort of delay, and you don't want that. How can you prevent that delay? Well, you can use the so-called acceleration techniques. The acceleration techniques, you can put basically an acceleration capacitance right here. This is R, this is C, this is RP, and this is 5 volts, and this is to ground. So what does this C does? Basically, in the rise time, C VC is charged to Vin minus VBE. So it has basically some charge stored here. It has some charge stored here. This charge will be immediately released like an impulse, like a very short impulse, to charge the parasitic capacitance, which is very, very low. But even with 1 nanofarad, you should be able to accelerate even more. So let me put here the faster version already with 1 nanofarad here. And let me rerun the simulation. So now you see that the delay has almost completely disappeared, and that's because basically you're gonna let me cancel this. So if you look at the green curve, you're gonna see a delay in the rise time, not in the fall. But if you put the 1 nanofarad here, you see that the delay has disappeared, almost disappeared. There is still some delay, but it has almost disappeared. And if you check the current here, you see that it is going to provide some milliamps. It's going to provide some milliamps to fasten this transistor here. You can even increase to 100 coulomb to 100 you don't have to increase so much, because otherwise it will be a capacitance to charge, and it will be very dangerous. So you'll be obtaining the opposite effect. So 500 pico, for instance, should be the perfect value to provide enough charge, but let's just say 1 nano is enough. So you can even provide these two acceleration capacitance right here, and also right here in the base of the transistor. You will speed up your MOSFET, you will speed up your transistor with. So as you can see, with the acceleration capacitance, the non-inverting level shifter does provide a better performance with the common gate level shifter. I don't know, maybe here I'm doing something wrong, but anyway, the inverting level shifter, it is the most common used solution, and it can even work. It can even work with even up to 100 kHz. Even though I would suggest for this kind of circuit to use the Texas Instrument integrated level shifter. So my suggestion is to use if the switching frequency of the signal is below 100 kHz, you are safe to assume that you can use the inverting NPN solution. But if the switching frequency of the signal is higher than even 1 MHz, well, you have to rely on some integrated circuits. The integrated circuits, integrated level shifter circuits, I will show you something. TSX Texas level shifter. I can show you some voltage translator, integrated voltage translator, which I used, and it was in the series of the TS6. Yes, it was this one. If I do remember, in my company I used this level. Don't care. So if you do watch the datasheet of this guy, how it is done inside. Come on. So as you can see, you have some circuits. Here you have some circuits called the one shot called gate bias and one shot accelerator, and as the name suggests, these are circuits which are used to this circuit here are used to provide the charge of your MOSFET. This is a common gate. This is a common gate. It is not reported, but this is a common gate MOSFET because it does not invert. It does not invert the shifter. So as you can see, this is the common gate configuration. It has a very low pull up here, and also a very low pull up even there, and it translates from VCE to VCB. So you're gonna have something like this to something like this, basically. The device is a fast gate architecture with edge rate accelerators, to improve the overall data rate. And it is an open tray application, so of course it is like intended. So you don't need to put the external resistor in this kind of circuit. And okay, this was what I was looking for. So as you can see, there is here you have the common gate, the common gate solution here, and you have the pull up with the one shot. This is a PMOS. Remember that it has the symbol here, and so you're gonna have the signal perfectly translated to how does the one-shot generator works? Basically, the output detects rising edges on the A port and the B port. So let me change the color. You detect the rising edge. You detect the rising edge here. Okay. During the rising edge, the one-shot turns on. So during the rising edge, T1 is on, and if this transistor is on, it will immediately conduct, and it will accelerate the circuit. During the rising edge, the one shot to turn on the P1 transistor for short duration speed after. So yes, it is basically what more or less what I said, and this is one of the most typical applications. So you have 1.8 volt from this side, and it will translate to 3.3 volt in this side here. So it will have a square wave here to a square wave between 3.3 volt. Very, very simple. Very, very simple to use. The OA stands for output enable, and you need to provide the pull down because maybe it is open something, don't remember. So this is it, guys. Thank you for your attention, and see you in the next video. Sorry, before closing the video, I will show you why you should use for frequency higher than 1 MHz, you should use this TSX or something, because well, let me put for instance 1 MHz here, and you will find out that even though you are using the acceleration capacitance, you see that the green output voltage does not stand a chance. You're losing almost 50% of the signal. So with 1 MHz, it is not safe to use a discrete made level shifter. So this is very funny though to see what is happening also in the other kind of circuit. So for 10 kHz, these circuits are for 1 kHz or 10 kHz. All these circuits are almost perfect, with major emphasis of the inverting level shifter. Thank you guys for your attention. Thank you guys for your attention, and see you in the next video.